Yeah, at the end of the last video, I was a bit mumbling, but I mean, if there are two cases that x is right, x is the answer and x prime is the answer, and then if E gets you to, I mean, this overlap area with then if your fx plus E is in here, it's difficult to actually distinguish between these two cases. So in either way you designate G, you will get the, you can actually compute that your error probability is a considerable number, which is not too small. Anyway, so that roughly give you the intuition why this Shannon theorem is best possibly true. But we can actually ensure a bit more. Let's say a group code is a coding scheme in which the map is linear. It means f of 0 is 0 and f of x plus x prime is f of x plus f of x prime. Of course, we take addition as a vector addition modulo 2. We are considering this concept because here the f could be complicated function. So there are 2 to the m choices here, and they could be mapped to this string of length n in some arbitrary way. Then, if you want to send actually a message, when x is given, then you actually compute fx and then send. And later decoding has to be done in similar way. And which actually takes some computation power. So you have 2 to the m vectors and you have to designate each one of them. But if your code is group code, then as long as you know, say 1, 0, 1, 0, 0, 0, so this standard basis vectors, and if you know its image, then once you are given arbitrary vector, you just add these 3 to compute it easily. So group code is better than just normal code in the aspect of computability. And theorem is that if you have a similar situation, P is between 0 and 0.5, and for given epsilon, there exists a group code with the rate of transmission greater than 1 minus h of p minus epsilon. And probability of incorrect transmission is less than epsilon. So this is obviously stronger than the Shannon's theorem, because there, we don't actually require the code to be a group code. But here, we are required to make it a group code. So how can we prove this? So as we are taking a probabilistic method course, we prove it using some probability. We want to take something at random. And what at random? So we want to find the function f, which is a group code. So we want to take a group code at random. And how does a group code defined? Defined in this way. So if you want to find a random group code, then what would you do? You take all standard basis vector, which is a 0, 1 string, which has only one, and every other digit are 0. And then we take image of this at random, which generates a group code. And we prove that if we generate f at random, then at least one of them is what we want. And how do we prove this? We generate f at random and measure the probability that when x and e are chosen at random, incorrect transmission. So we want to find f such that this is smaller than epsilon. Then what we can do is we generate f at random, x at random, e at random, everything at random, and we show that the probability of incorrect transmission is less than epsilon. If we prove this, then that's same as summation of f, all f, the number of possible f. Summation of here, probability xe of this is smaller than random. Then means on average there exists one f whose probability of incorrect transmission is smaller than epsilon. So that's what we plan to do. So again, additions and subtractions are all modular too. And let delta be small so that p plus delta is still smaller than 0.5. And h of p plus delta is smaller than hp plus say epsilon over 2. And let n be large and m be n times 1 minus h of p plus epsilon. And let ui be the standard basis vector with 1 in the ith position and the left 0. And we let f of u1 to um be chosen independently at random. Independently uniformly at random. From a vector of length n, 0, 1 vector of length n. And naturally, to make it as a group code, for each 0, 1 vector of length m, we simply let f of x be the summation of xi, fui. Then this defines a group code. And now we need to define a decoding function. What would you do? One natural thing is that you have to, here, 0, 1 to the m, here 0, 1 to the n, x prime, f of x prime. E was added, so now your y is here. Then what you do is you take the closest one. It's likely that if there are two points here, f of x prime, and e is added, then p is smaller than half, so it's likely that it's closer to this fx. Somehow it's closer. So we take the decoding function, G from n-digit string to m-digit string by setting Gy equal x if x is somewhat close, and this close can be actually measured, that this y lies distance at most, say, np. Here distance is again Hamming distance, the number of digits which are different. So, but if there are more than one such choice, then we are at a failure, because in that case there is no good way to distinguish whether it's coming from x or x prime. So if x is a unique vector with length m, whose image fx is actually Hamming distance and most, say, n times p plus delta from y. By adding this delta, we make sure that most likely your fx from plus e is not so far from fx. So in average, it's fx plus e. In average, its distance is np, but by adding delta, we make sure that with high probability it's at most this radius from the fx. If there is no such unique x, or more than one such choice, then we consider the decoding to be incorrect. Or equivalently, you can just assign any number, but this way is easier to analyze. Then simply, here there are two ways in which the decoding to be incorrect. First is that f of x plus e is Hamming distance more than n times p plus delta from fx, or there is x prime which is different from x with fx and fx prime are close. Let me do something and then come back in a minute.